Today I want to show you Quarch Power Studio, or QPS. This is the main application for working with the wide range of power analysis products that we make at Quarch. So we make several different range of products. This can be, as we're going to use first, our HD range of programmable power modules, primarily designed for the storage industry, for testing SSDs and hard disks. It can also be used for PCIe, card and other devices. Beyond that, we can also use our PAM system to capture both analog and digitals from SSDs, both their power and the digital sidebands. We can capture GPU power consumption, including the external PCIe connectors. And we even go up to the AC world for capture of both single and three-phase mains devices. At this point, we could be talking about anything from a server to a rack of servers to an EV charger or even an electric motor. However, first of all, we're going to start with the HD module I have connected to the system here. So we select it from the connection screen and we're ready to go immediately. So the first thing we want to do is choose our sample rate. I'm going to start at a millisecond sampling, so that's 1,000 samples per second. I have attached to this a hard disk, so if I begin recording, we start to see the trace data. I can also open up the summary pane on the right hand side. We can see that the real-time values are all very low. This is turned off at the moment. So this fixture has power control, so I can obviously the programmable power module can both supply and measure, so we can do margining, ramping, glitching, power loss and brownout and similar. In this case, I'm just going to use it to turn the drive on. Now, in the top window, we see the latest data coming in, and on the bottom, the timeline window, we see the longer term view of the trace and what's happened. You can see that the voltages, the blue and red line, jumped up immediately when I pressed on. And then we can see the current and power steadily ramped up as the motor began to run. And then we've got spikes here showing probably the head movement of the drive. Finally, we settle into a fairly stable state. On the right hand side now, you can see we're drawing about 3 watts of power and 12 volts and about 1.9 on the 5 volt rail. So this is a dual rail drive. We're capturing both rails at once. So navigation is very simple. I can either leave this trace running more or less as long as I want. Unlike a scope, we're not limited in capture time, but I've got what I want for now, so I'm just going to stop this. One of the major advantages of Power Studio is this long-term capture. Rather than getting a small scope snapshot, having to view that on a little screen, maybe copy something manually off onto a USB stick, we're able to stream all this data back to the PC, so the only real limitation is the size of your disk drive. And we can then jump back and forwards and look in detail at what's going on in the trace. So I can scrub through this quickly. You can see some interesting changes in the power. If I see something I want here, I can draw a box around it, zoom right in more detail. Double clicking again moves us around the timeline. If we want to increase the chart width, then I can increase that to a set level. Let's see if there's anything interesting going on here. Okay, so let's say that this doesn't give us enough resolution. Let's step up. So this device can capture all the way down to 4 microsecond samples, or 250 kilosamples per second. So that's enough to see a lot of the small details of what's happening. So I'm going to turn the drive off, let it spin down just for a moment, and then we'll create another recording. So let's go for a 200 millisecond window again, start recording, and turn the power on. Now this time we're capturing a vast amount more data than we had previously, a larger number of samples, a lot more detail. When we were using 1 millisecond sampling, then we were averaging all the 4 microsecond samples together. This time we are capturing every single sample and displaying it, and so we can see a lot more detail of what's going on. Now I've just made a short recording here, just so it's easier, but we can start to see the slow ramp up of the power. But what else we can see is now we can look right in at the level of detail on, for instance, the spikes of inrush current as the drive came up. Now in this case, the inrush current is actually pretty low. But we are talking about up to about sort of 15 watts or thereabouts, so it's not insignificant. Let's zoom in a little bit further. I check the channels here, we see, okay, so the current is actually coming about 1.6 amps. So I want to measure this in a bit more detail. So what can I do? Well, I can either go over the summary tab here and just highlight over this. So I can see 1.6 amps are, but of course at this point the voltage is very low, so our actual power consumption is going to be very low as well. Other ways of measuring this, I could bring in cursors. So I can bring a cursor down to what I'm interested in measuring and either read directly off the chart axes, or I could open up the cursors tab and we can read the current and voltage off the bottom section here. If I'm interested more in what's happening on the other axis, I can pull in a second cursor, and then we get the vertical cursor positions as well. If we're done with these, you just click, we'll put the cursors away again. So navigating around here is relatively simple. We can see pretty much everything we want. If I want to measure the delta, for instance, between two things, let's look at what this size of this gap here was. Presumably the drive dropped into a more idle state for a brief period of time. I can see there that's about 0.03 seconds. So what else can we do? Well, for a start, if there is more than you're interested in here, let's say for instance we don't particularly care about the voltage, you just turn the voltage rails off. We can consider just current and power, or for just power. If we're not interested in the individual rails, for instance, I could take them off as well, and we'll just focus on the total power. So the right hand side here gives you lots of options for how we look at the trace. So the summary view tells us either the real-time value when we're streaming, or when we stop streaming, the value under the cursor. Channels allows us to show and hide the channels. You can also change the colors to suit. In the statistics tab, we can see the real-time statistics. So in this case, we've got most of the channels turned off. Turn them back on again. So this is showing us the statistics of what is on screen at the moment. So we've got min, max, and mean for all the various different channels that are here. Finally, we've got the cursors tab that we looked at before, and then we have annotations. So as well as just looking at the data, this software is designed to help you analyze and share it. So for instance, we could drop an annotation at the start of the trace here on power up, and we can edit the annotation and give it a name, and there we go. Now we could move to another point in the trace where something interesting has happened. So for instance, here is the point that we assume probably the motor has begun to spin up, so I could add an annotation in here. Let's call it spin up. So we've got two basic annotations on the trace. We can see them here. We can click on them to jump straight to them, but we can also calculate statistics across these annotations. So in addition to the basic statistics values here showing you the stats on the screen, we can open up a statistics grid. Now this shows you a lot more detail. Here we split out the statistics based on each of the annotations. So the first one is from the start of the recording to our first annotation, and then we have from the first power up annotation to the second, and the second annotation to the end of the trace. There are a lot of different statistics here. This is min, max, mean, and energy for all the various different channels. And by clicking the little plus on the right hand side, we can add or remove these as you want. So for instance, if we're not interested in voltage current, we can just take those out. Within each of the rails, we can configure these as well. So let's just say we only want total power, min, max, and mean. That sounds good. And we'll keep total energy on as well. So we've turned this into a much smaller set to look at. So during the spin up section to the end, for instance, we did actually get a negative power consumption there. The drive is quite inductive, so that's definitely possible. However, the maximum power is significantly higher. Let's change it into watts, and we can see so 43 watts during the spin up, so that's fairly significant. And we've got the mean power there as well. And I did turn the energy off. I'll turn it back on. So the energy then shows us the number of joules consumed in energy terms in that period. So there we go. 15 joules of energy was consumed between the time we dropped our annotation for spin up and the end of the trace. So let's close that. So on the top bar here, we've got more controls. We can hide and show the annotations. We can save this trace. So by default, when you start a new recording, it will delete the old one, but this allows us to save and maintain our analysis file for later. We can also take snapshots of the screen and share them quickly. For devices that have power control, we can turn that on and off here. Obviously, we can start a recording. We can set our sampling time, so there are a bunch of default sampling rates in here, but if you want something else, you can enter a different time. Now, in every case, this device is sampling every single 4 microseconds regardless. If we ask, for instance, for 16 microseconds, what it will do is it will take 4 microsecond samples, average them together, and give you then a single sample. Now, what that means is, if you ask for a slower sample rate, we're never throwing away data. We're always averaging together, so we get very accurate power readings. Now, this particular device is multi-rate, or at least it can be multi-rate. Sorry, this one is not. This is a single-rate device. As we can see here, there's only one group. It is the analogs, and it's currently set to 16. If you had a multi-rate device, that is the case where we have analogs and digitals on our PAM range. Then you could individually set the 2 groups here. So for instance, on the PAM devices, mostly we have analogs will run up to 250 kilohertz and the digitals can run up to 1 megahertz. And we can tune both of these separately depending the resolution of data that you need. Okay, so let's pick up, actually no. Okay, so let's start on the left-hand side tab. So the right-hand side is all about viewing the data and working out what we have. The left-hand side is more on control. So again, we have a replication of the output enable control for power. This device is capable of powering both SAS, SATA and NVMe devices, NVMe using 12 and 3.3 volts. So there's a configuration for that in here. We can set the output voltages, so we can tune the exact voltage with this device for the drive, so we can overvolt and undervolt. All these controls are on here as well. We control both channels individually, and we also have additional protection for the drive you can set separately to avoid going into an accidental overvoltage and damaging it. The output pull down turns the power supply into a 2-quadrant supply, so we can actually sync current as well as source it. That means if you drop the voltage, the rail is actively pulled down. That creates a much more aggressive test on the drive. Now, you will get different controls in here depending on the device you're attached to. Our AC devices, for instance, do not have power control. Our PAM devices do not have power generation or power output, so they wouldn't have the controls here for that. On the recording time, again, we've got some simple replication of the controls in the top bar. You can also set a limited recording time, for instance, record for 5 minutes and then stop. It just means you can leave your desk and be sure you're not going to fill up your drive accidentally. When you are using trigger functions, we have the ability to pre-trigger a percentage of the onboard RAM. We can set our trigger sources as well. So the record trigger by default is manual. That means we press the record button, we start immediately. But you can set to record on various different sources depending on the module you're attached to. Pattern, for instance, is limited to the ppm, and this is a generated voltage pattern that we can create. In this case, if we use this trigger, it means when we start the voltage pattern, which for instance could be a ramp up of power rather than just turning it on, then recording would also start. We can also start recording automatically on turning power on. We can do so from an external trigger in. And we can also do so if the drive exceeds a set threshold. So for instance, we could set a voltage or current threshold on this device and say we're not going to start recording until you go above that. And in that case, of course, the pre-trigger would then give us a view over what had happened before the trigger actually occurred. Some devices also have channel enable, so you can actually turn off things that you don't want. We can turn off power here, for instance, if we don't want automatic calculation of power. More likely we'd probably be turning off just one of the voltage rails if we had a device that only used a single one. Now, synthetic channels is a relatively new feature for QPS. It came out in the last year. This allows us to create a range of additional channels based on the data that's already there. So if we look at adding a new channel, for instance, we can decide what group it's going to go into. So for instance, in this case, we could select the power group. We could call it RMS power. There we go. We choose one of the standard functions. In this case, we're going to use the RMS function with a, let's say, a 200 millisecond window. And we want this to go back into the power group again. We want this to be sourced from the 5-volt power. So in this case, what we're going to do is we are going to be recording with a 16 microsecond sampling rate. However, we're then going to create another power channel, which is averaged down to 200 milliseconds. So that allows us to get the detail view and a longer term average at the same time. So let's just run this again. 1, 2. You can see what we have in here is RMS power is also being shown. I'll just stop that here. So let's turn some of these off. So what we're really interested in is just the ones that we want to compare here. There we go. So what you're seeing here is the purple trace is the 16 microsecond sampling, and then the orange trace is the 200 millisecond average across that. So that gives you a useful ability to see the trends over time, along with still being able to zoom into some of the really small details as to what's going on this device. If we click the full control down here, it will immediately drop back to the default chart width that we've set earlier. So we spoke about the pattern tab already. Here we can work with the programmable power module to slew the output in a pattern. So in this case, I am going to add a pattern, which is so 1 millisecond after running the pattern. We want the voltage to go from the current voltage, which is at 0 millivolts because the power is turned off. We want to turn it on fully, so we're going to go to 5,000 millivolts immediately. On the 12 volt pattern though, we are going to delay that to 10 milliseconds, and let's say that's when we'll begin to ramp up. However, then we want to ramp up over a 100 millisecond period. We want to go to 12 volts as we'd expect in that channel. We want to interpolate it. Now what that means is our first rail is going to jump up very quickly. Our second rail is going to be both delayed and also ramp up more slowly. To begin, we want the power on. However, we want to zero the outputs. So the output voltages are set to 0. We are in an output enabled state. However, we are not supplying voltage to the drive. Now when we run the pattern, hopefully it'll work. So let's just hide that again. I'm going to start recording, run the pattern. That looks much better. So let's zoom in here. So what we see now is the 2 voltage rails starting at a different time. So first of all, our 5 volt rail goes up, then after the specified delay, the 12 volt begins to ramp, and it ramps up neatly. So with this we can create a wide variety of scenarios on the drive, everything from power glitches to brownouts to ramp rates, etc. So finally, on the triggering tab, we have options for trigger out. So we can choose to fire off an external trigger, which you can use to trigger another device. We can do that from running the pattern, from changing the power, from starting a recording, or from going over a threshold. And for instance, this could be used to trigger an analyzer to capture a trace or something of that sort. The thresholds are set per channel. So we can set a threshold level, either rising or falling polarity for any number of the channels, and if any of those thresholds are exceeded, the trigger out will happen, or the recording will start, depending on how we've configured it. So a few other things we can look at here. As I said before, we can save this trace and share it with people easily. We can open an existing recording that we've got, and we'll try that later. We can also export the data. So for instance, we can export the current selection as a new trace. And at the moment that would be very small, but if I was to select, for instance, a specific region here that I was interested in, then I could export just that section either as a new trace file, so a compressed binary file that we can open in Power Studio, or a CSV. So we can have all that data in what could potentially be an enormous CSV file, but in a great format for doing post-processing with pandas or similar. We have application preferences. So we can change everything from the volley precision to the format of the chart axes, to the color themes, to what we do with recording files, where we place them, whether we delete them, and then change notifications and debug logging if that's required. So let's start with a more interesting recording. So at the moment we've only been looking at this hard disk that's powering up, but we have a whole range of other devices here that we can look at. So let's start with an AC trace. So this is a capture of the fridge in our office on one of our newer AC range of devices. So here, this is running 125 microsecond sampling, or 8 kilosamples. This is an AC device. It is very different. However, the software and all the controls are basically the same. We've got some annotation, so this is when the fridge door was opened, this is when the compressor started, and this is where we pulled power, for example. We can jump around and see those points. Now, we start to see some interesting things here, though. So this pinky purple trace here is the AC voltage waveform, and at the point the power was pulled, it doesn't just disappear. It actually starts to decay slowly, which is really interesting. And not only does it decay in amplitude, it's also slowing down in frequency. And what's actually happening here is that the compressor in the fridge is continuing to spin, and it's actually feeding voltage backwards again until it stops entirely. Now in this case, that looks quite nice. It's a steady dropping of the voltage. However, there are cases and devices where you turn something off suddenly and you actually get a very large spike instead. And large spikes would also be seen here, and they're the kind of thing that could actually cause damage to products over time, and are very useful to be able to see at this level of resolution. So there are many different ways of capturing AC. You can use a simple watt meter to give you a basic second-by-second indication of what's happening. You can use a complex power analyzer. You can use scope and current probes, but many of these devices are either not very good in terms of the data we get, or they can't be automated, or they're not very accurate, or they're very expensive and hard to set up and need direct mains connections and probes in place, which can be both difficult and potentially dangerous. In the case of the Quarch AC PAMs, they're all plug and play. You push the connector on either side, we sit in line in the power cable, and you're ready to go in seconds. So AC devices have rather different channels. We have the instantaneous voltage, we have the RMS voltage, we then have similar for current and power. Now this is where synthetic channels really come in. So it's not on this trace, but on our on newer traces that we've captured, we can have a range of synthetic channels, including things like total harmonic distortion, crest factor, and many others. And this gives us a very good ability to look at additional things that are going on in the device. Now this is a 3-phase device here. So we can see L1, L2 and L3 are the 3 different phases. So we just turn current and power off for a moment. You'll see that although this is the 3-phase device, we only have in practice a single phase. Because we're measuring a fridge, there's nothing else here. AC PAMs, they're all plug and play. You push the connector on either side, we sit in line in the power cable, and you're ready to go in seconds. So AC devices have rather different channels. We have the instantaneous voltage, we have the RMS voltage, we then have similar for current and power. Now this is where synthetic channels really come in. So it's not on this trace, but on our on newer traces that we've captured, we can have a range of synthetic channels, including things like total harmonic distortion, crest factor, and many others. And this gives us a very good ability to look at additional things that are going on in the device. Now this is a 3-phase device here. So we can see L1, L2 and L3 are the 3 different phases. So we just turn current and power off for a moment. You'll see that although this is the 3-phase device, we only have in practice a single phase. Because we're measuring a fridge, there's nothing else here. If we were to open something else, So let's have a little look at EV charging. So in this case, we have used a 3-phase AC power analysis module to capture charging on an EV. So let's bring that up. Now in this case, we've got a lot of synthetic channels here as well. So we have various filtered channels, we've got harmonics, we've got frequency, phase, we've got active and reactive power, we've got THD or total harmonic distortion, VA and VAR. So all the standard things that you'd be interested in as an expert in mains are going to be available to you here. It does mean there are a lot of axes, but of course we can turn these off when they're not of interest. We can just drop out power factor, for instance, if that's something that you don't really care about. What we do have here, of course, is we are now getting all 3 phases. So this is the initial startup. Let's just zoom into that a bit more so we can see what's going on. And we can see the very small ramp up here at the start, and then we rapidly stabilize the AC waveform nicely. So let's just turn off that for a second and look, for instance, at power factor. So the power factor here is relatively stable. We are sitting at about 98, heading 99% power factor. So that's looking really good. So this charger has the current waveform expected to line up very closely with the voltage. So let's just take off everything that doesn't matter here. So we've got, let's just go with the single current waveform and the single voltage waveform, and we can see these stack very neatly on top of each other. They are in phase with each other, so that's why we have the high quality power factor. Checking for updates is a good idea. We do release new versions of the software very frequently, so it's great to keep up to date with the latest features. Another important thing to note is that this software can be fully automated. That we can do in Power Studio can also be automated easily from Python. Using our Quarch Python package, you can do everything from opening the application, setting up the device, starting a recording. You can add annotations directly from script. You can even add custom user channels. For instance, something like a temperature channel based on the heat that your device is running at or its performance can be added into that trace, so we can look at power and performance at the same time. You can then export, save as, you can access both the raw CSV data and the calculated statistics all directly from your Python script. What that means is you can be running tests 24/7. You can run all your tests overnight perhaps, and then you can come back in the morning and spend your time analysing the high quality, neatly annotated traces that you have taken, rather than spending your time doing frustrating manual testing, as is often the case. So Power Studio really gives you an entirely new workflow, both in terms of its very long-term capture, which can be anything from minutes, hours, or even days. The ability to visualize the data and see what's going on. The human eye is incredible at picking up little details and asking the question of, well, what happened here? Why did we get this spike? Why did we get this change? Being able to share as well, being able to take screenshots and or just email traces to each other, incredibly useful again. It's amazing the number of cases that we've seen where customers have shared data with us, which is effectively using a mobile phone to take a picture of their oscilloscope screen. Often in low resolution, hard to read. And in almost every case, we've had to go back and say, could you please take a Power Studio trace in high resolution? And then we've been able to look at it and go, okay, yeah, we can help you and understand what's happening here. And that ability to look into the data is incredibly valuable. The software, the automation, the example application notes on our website are all available free of charge, so please download them and get started. If you do have any questions, you can always email us on support@quarch.com. We'll be happy to give you some tips on how to get the best out of your device or handle any problems you might have come across.